Good morning. In this video, we are going to learn about Scherrer's plot. So, to know more about Scherrer's plot, you should check the note which I provided to you. In Scherrer's plot, mainly the broadening due to the crystalline size or nanocrystalline size is taken into account, but strain involved due to nanocrystalline size effect is not exactly taken into account. The strain effect is considered in Williamson-Hall's equation and plot. Okay, so for Scherrer plot, the formula is capital D is equal to 0.9 lambda divided by beta cos theta, where D is the particle size and lambda is the wavelength of X-rays, beta is the full width half maxima of a peak, and theta is the half of the angle of diffraction. So what this is origin, and so what I am going to do is I am going to import a set of data. So excited test data. So the data has been imported. Let me plot the data. Okay, we have the X-ray diffraction data here. So now what I'm going to do is I'm going to change the scale according to our convenience. So I will start from suppose 28 to 72 for x-axis, then for y-axis let me choose the values from -10 to around suppose 1550. So you can change it or you may leave it as it is. I'm changing so that now the pics look quite better. Okay, now there are 9 peaks and we are going to do multiple peak fitting, which you can do from analysis, fit multiple peaks. So Lorentzian fitting we will do, we have 9 peaks already. This was done in another demonstration earlier. So I'm clicking OK. Dialog box appears. Please double click on the centers of the peaks. So I choose OK. Then let me choose the peak 1, double click. Peak 2, double peak 3. So this way I'll go on double clicking each peak which is seen. Now another dialog box appears which says please roughly validate the width of peaks. So I am not going to change anything. I'm just doing OK, and you can see that all the 9 peaks are fitted here. So let us find out the peak fitting data. So I'm going to multiple fit report. I'm scrolling down to find more information about the peaks. So here we have area column, center, width, and height columns. Okay. So out of these 4 columns, 2 columns are of particular interest for us. One is the center column, and then the other one is the width column. Okay, center means the 2 theta values which are plotted along x-axis, and width means the full width half maxima of the peaks. Okay. So next I'm going to show you. So for Scherrer's plot, so what we are going to plot, we are going to plot 1 by beta versus cos theta. So cos theta will be plotted along x-axis and 1 by beta will be plotted along y-axis. So I'm going to the Excel sheet and I will explain from there what are various quantities which are required for Scherrer's plot. Sheet, and here 2 theta values, these 2 theta values have been taken from origin, and full width half maxima beta values have been also taken from origin, and they are initially in degrees actually, but later we have to convert them to origin. Okay, so from 2 theta degrees we are converting them to theta degrees. Okay, similarly you find the values, all the angle values from to convert them from 2 theta to theta values. Okay, then one you have find them find 2 theta degrees theta degrees. from 2 theta, then you find these degree values, you convert these degree values to radian values. So you can see in the formula box, so these values have been converted to radian values. Okay, now let's come to the full width half maxima degree values. So these are various degree values of full width half maxima. So they have to be converted to radian values. Okay, so here you can see here, if I click here, then radian d6. So this is the d6 column, as you can see. So the degree values have been converted to radian values, and now we have to find the 1 by beta value. So 1 by beta value, why we have to find the 1 by beta values? For that, you can go back to the note which has been provided to you, because Scherrer plot is done between cos theta and 1 by beta. So 1 by beta values is just 1 divided by this particular column, which is G6 column. Similarly, you find all 1 by beta values, and then you have to find cos theta values. Cos theta values have to be plotted along the x-axis. So in order to find cos theta values, this is the theta radian. Cos theta values cos of f6. This is the column f6. So you find all cos theta values. Okay, so now we have to go back to origin and plot these cos theta values along x-axis and 1 by beta values along y-axis. Okay, so I'll go back to origin now, and I will show the rest of the demonstration from there. And here here cos theta values have been plotted along the x-axis, and along the y-axis 1 by beta values have been plotted. So let us just do the plot and see what we get. So we get some scattering results like this. So along the x-axis we have cos theta values, theta values, and along the y-axis we have 1 by beta values. So 1 over beta values. Okay, so these are the points, and let us do linear fitting here. So I'm going to analysis. So fitting, do linear fit, open dialog, and then I'm not going to change anything here in this set of instructions, and I'm doing okay. So we have the linear fitting here. Along y-axis, and 1 by beta values along, sorry, cos theta values along x-axis, and 1 by beta values along y-axis. So let us do the plot. So what we can do linear plot with all these points, or if you think that this particular point is quite far away from other points, then you can also delete one particular set of points from this table. Okay, so anyway, I'm not going to change anything. I'm just going to do linear fitting, and fitting fit linear. So I am not going to change anything. So okay, so here we have the linear fitted values, and I'm just expanding this. Okay, so slope, we need to find the value of the slope, which is 497.30, and if you once know the slope, we can find the value of the average particle size. Because if you see that Scherrer plot is actually represents that of a straight line, and from this slope value average particle size can be calculated. However, you can make this fitting better if you can just delete one point, maybe this particular point. In that case, this adjusted R square value will increase, and we'll get maybe slightly different value of slope.